Gauss's law always lets you say something about the amount of electric flux passing through a closed surface. Under certain circumstances, it also lets you solve for the electric field made by an object. Typically, those circumstances involve charge distributions that have certain kinds of symmetry: spherical, cylindrical, or planar. We're going to work through an example involving a cylindrically symmetric distribution of charge. Here's a long cylinder of radius capital R, filled with a non-uniform charge distribution. I'm drawing it as a fairly short cylinder for convenience, but consider it to go out in either direction for a while. We'll let the volume charge distribution be ρ equals A times R squared. Ρ represents a charge per volume, and as written represents an object that has charges concentrated preferentially toward the edges, which is a fairly reasonable thing to find in reality. Okay, let's work through the problem-solving procedure in detail. The first and second steps, in no particular order, are to draw a picture and write down the fundamental equation we're going to use, which we've done. Now, remember what our goal is. We're trying to solve for E, which means we need to somehow get it out of this integral. That's where the symmetry of the situation comes in. The charge distribution ρ depends only on R, so you can rotate the cylinder any way you please, slide it back and forth, or flip it lengthwise without making it look any different. And that means that the electric field that this object makes has to have the same properties. It can't have field components that disrespect those symmetries. In fact, the only field that's consistent with the symmetry of this charge distribution is one that's strictly radial. So without doing any calculations, we can conclude that the electric field made by this object must be strictly radial, pointing outwards if the charge distribution is positive, and its magnitude must depend at most on R. The next step is to draw a Gaussian surface. Again, Gauss's law is a statement about the flux through some arbitrary surface, and it's going to give you information about the E field on that surface and nowhere else. So if you want to know the E field right here, you better draw a Gaussian surface that includes that point. And it's probably a good idea to draw a surface that has the same kind of symmetry as the charge distribution, for reasons we'll see right now. With the surface drawn as so, the differential area vector at any point on the end caps points along the axis. Meaning that out there, dA and E are perpendicular. And that means on the end caps, E dot dA is 0, and we can ignore those end caps forevermore. But all along that middle section, E and dA end up being always parallel, so they dot to give just the magnitudes of E and dA multiplied together. Note that I've written side under the integral sign to indicate that we're integrating over the cylinder but not including the end caps. Okay, next step. We've decided that the E field can depend only on R, and the part of the cylinder that we're still considering exists entirely at one fixed R. And so the E field must be of the same magnitude everywhere on that surface, which is to say it's constant over the domain of integration. And so we pull it out. And the integral of dA is just A, which in this case is the area of the side part of a cylinder, which is 2 pi RL. L is a totally arbitrary length, and we won't worry too much about it. In the end, it's going to cancel out. So at this point, we've dealt with the left-hand side of Gauss's law and can isolate E. Now we deal with the right-hand side of Gauss's law. We figure out the total charge enclosed by our surface. I'll redraw the picture and shade in the actual charge enclosed. Note that it only occupies some of the volume enclosed by the Gaussian surface. We're given the charge density ρ, and to get the total charge q, we're going to integrate up a bunch of dq's. Each dq can be written as a density times a differential volume dv. The dv represents us breaking up the cylinder into lots of bits, and there are lots of different ways we could break a cylinder up into bits, shells and disks among them. Our ρ depends on r, so we want a dv that has one single r associated with it. Shells are our best bet here. And we can get the volume of a shell by taking the area of that shell and multiplying by the thickness dr. So our dv is 2 pi rl dr. Quick check, dv should have units of volume, and our dv has an r, an l, and a dr. That's 3 length units, or volume. We'll put things together. Now we figure out the bounds of the integral. The charge distribution begins at r equals 0 and ends at r equals capital R. So we put that in and execute. Plug in that q enclosed and we can solve for the total E field. The L's canceled, as they should since they were arbitrary, and we get a big R to the 4th over 4 epsilon naught little r. So that's the E field at any point outside the cylinder. What if we want to find the E field inside the cylinder? Well, in that case, we need to wind things back and use a different Gaussian surface, one that includes a point inside the cylinder. With this new Gaussian surface, most of the steps proceed in exactly the same way as before. I encourage you to check that out for yourself, one step at a time. What we end up with is that E equals q enclosed over 2 pi rl epsilon naught once again. What's slightly different this time is q enclosed. Our Gaussian surface no longer encloses all of the charge. It stops short of the surface. So I'm going to set up the integral for q enclosed using an r prime as the variable of integration, so I can write little r as the upper bound. The charge begins at r prime equals 0 and ends at r prime equals little r. When I crank that out, I get a q that's a function of little r, meaning that I get some cancellations that we didn't have before. And the E field is now fundamentally different, depending on r cubed instead of 1 over r. So that's the whole procedure for finding fields with Gauss's law. Other problems might have different geometries, but they'll go basically the same way.